You might hear people say that OpenBSD is hard, or that math is hard. Often this phrase comes up in discussions about the operating system and its reputation for extreme security. But when you hear this, do not think of arithmetic or algebra. This is not about solving equations on a chalkboard. This is about the cost of trust in software. The narrative that math is hard within the OpenBSD community highlights a systemic difficulty in formal verification and complex logic reasoning within the operating system, rather than a lack of mathematical capability in the codebase itself. It suggests that even highly secure, formally verified projects face significant hurdles when scaling rigorous mathematical proofs to real-world, complex software stacks. To understand this, we have to look past the myths and examine the specific architectural trade-offs that define the platform. Consider the choice of programming language. OpenBSD relies heavily on the C language. Many modern systems move toward C++ because of its rich feature set and object-oriented capabilities. However, OpenBSD developers prioritize predictability over convenience. C++ introduces complexity through templates, inheritance, and hidden initialization sequences that make it difficult to prove a program will behave exactly as intended. In the world of security, you cannot afford hidden behaviors. Every line of code must be auditable. When you choose C, you are choosing a language where the rules are simple enough to be verified by a human or a machine-proof checker. This forces engineers to write more defensive, simpler code. It is a trade-off that sacrifices some development speed for a higher guarantee of correctness. This leads us to the concept of formal verification. This is where the math comes in. Formal verification uses mathematical logic to prove that a system meets its specifications. In the case of OpenBSD, researchers have demonstrated the application of formal mathematics to verify device drivers within the CL4 microkernel. They use a tool called Isabelle to ensure code correctness and security. This is not theoretical. It is a rigorous process where every function call and memory access is accounted for in a logical model. The persistence of this theme in OpenBSD communities suggests that even highly secure, formally verified projects like CL4 drivers face significant hurdles when scaling rigorous mathematical proofs to real-world, complex software stacks. The difficulty is not in the math itself, but in the gap between the ideal mathematical model and the messy reality of hardware and user input. Now consider the impact on the engineers who work on this system. Junior engineers often struggle because they cannot rely on standard libraries or third-party dependencies like SDL3 that can introduce unverified complexity. In a typical development environment, you might download a package and assume it works. In this ecosystem, the cost of error is high. You have to vet every dependency. You have to write code that assumes the worst-case scenario. This is known as default denial. It means that unless a specific action is explicitly permitted, it is forbidden. This forces a mindset where you must constantly reason about the flow of data and the potential for exploitation. It is exhausting work. It is why the community talks about the hardness of the task. This connects to a broader observation found in recent research regarding mathematical reasoning. There is a shared bottleneck between operating system security and artificial intelligence. Recent discussions indicate that the hardness of math in this context is often exacerbated by the rigorous constraints of the OpenBSD ecosystem. Separately, researchers investigate the inherent hardness of math problems for reinforcement learning, utilizing topological difficulty measures to define complexity. While all sources agree that formal methods are essential for bridging gaps in model understanding and system reliability, they differ in domain. One targets natural language reasoning, another focuses on operating system security, and the third analyzes algorithmic complexity. A significant knowledge gap remains regarding the intersection of these fields. The juxtaposition of OpenBSD's strict security model with the general struggle of AI models to solve math story problems reveals a shared bottleneck. It is the gap between symbolic reasoning and practical, noisy application environments. AI models often struggle to solve math story problems because they lack the ability to model situations and actions explicitly. Similarly, operating system engineers struggle when they cannot model every possible state of the system. The complexity of mathematical reasoning is not just about calculating numbers. It is about mapping out every possible path a system can take and proving that none of them lead to a security breach. This is why the community emphasizes defensive coding. It is not just about writing code that works. It is about writing code that can be proven to work under all conditions. Future implications suggest that as OpenBSD continues to adopt more complex subsystems, the community will likely pivot towards more automated formal verification tools or stricter dependency vetting to overcome the inherent difficulty of maintaining mathematical correctness at scale. The goal is not to eliminate the difficulty, but to manage it. The tools are becoming more powerful, but the fundamental challenge remains. You cannot automate away the need for rigorous thought. The system requires a level of scrutiny that most modern software development does not demand. This is why the stories persist. They are not myths. They are reports on the reality of building a system where security is the primary goal. Think about the implications for the people who use this software. When you run an OpenBSD system, you are running software that has been subjected to a level of scrutiny that most other operating systems do not undergo. The audit logs are detailed. The code is simple. The dependencies are minimal. This comes at a price. It takes longer to develop features. It takes more effort to maintain the system. But for many, the trade-off is worth it. They value the assurance that comes from knowing the system has been mathematically analyzed for correctness. They value the knowledge that a junior engineer is forced to write code that is easier to understand and harder to exploit. This is the core of the story. It is not about magic. It is about discipline. It is about accepting that some problems are hard and that the only way to solve them is to slow down and think carefully. The narrative of math being hard is a reminder that security is not a feature you add. It is a property you build through rigorous engineering. It is a property that requires constant vigilance and a willingness to say no to convenient solutions. As we look to the future of software security, the lessons from OpenBSD are clear. We cannot rely on the hope that code is safe. We must rely on the proof that it is safe, and that proof is hard to come by. But it is the only way to ensure that the systems we depend on will not fail when it matters most. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.